Hello everyone, I'm Jarkko Peltomäki. I'm from Åbo Academy University. And what I'd like to tell you is about how to use generative adversarial networks for test generation. This is a joint work with Frankie Spencer and Ivan Pores, also from Åbo Academy University. So the aim of this talk is to tell you how to generate test suites with generative adversarial networks, that is GANs, in an online fashion. And just a few words about the assumptions. So we assume that the system under test, it's some sort of a deterministic black box mapping from an input space to an output space. So we output vectors. And as is common, especially with cyber-physical systems, we have some requirements for our SUT. And here we assume that they are given as a fitness function f, taking values between 0 and 1, with the property that the test from the input space I is falsified if and only if its fitness equals 1. So high fitness tests are the same as challenging tests here. Moreover, we assume that evaluating these SUTs is expensive. So then a few words about GANs. So I don't really have the time to explain them in detail, but here are some broad ideas. So consider the input space and some probability distribution P on it. And a generator, say G, it's a mapping from an auxiliary space I prime to this input space with the property that it transforms some distribution on I prime, say the uniform distribution, to this target distribution P on the input space, which we would like to sample from. And said in other words, if we want to sample according to this distribution P, we would do the following. So instead we sample uniformly on this auxiliary space I prime, and then we map those samples via this map G, and then we get samples on I that are actually distributed according to this P. That's the purpose of a generator. And here we are all the time talking about Wasserstein Generative Adversarial networks, but it's just a way to train this G based on a large data sample from P. There are other ways, but in this paper, we focus on these ones. And how to then use this for testing? Well, consider this set. This is the set of challenging tests for our SUT. So what we would like to have is a generator for this set. So like if we had such a thing, we could sample uniformly on this one, then we are basically done. We can find the test suite simply by using this generator. So we would like to have something like this. The problem here is that, okay, how do we train the generator? Cannot really do it in a traditional way because it needs a large data sample from the input space according to this target distribution, and we don't have it. So what instead we need to do is train this Wasserstein GAN in some online fashion. And this paper is basically our proposal, how would you could do it. And let me first explain some broad ideas how this is done. So first we obtain some random sample of tests. Then we train a Wasserstein GAN with these tests. We can do it now that we have data. We don't use all of the data necessarily. We just use high fitness tests from the random sample, whatever high fitness means. And then our aim is really to make this test suite larger. So we would like to add test suite. So how do we find new tests? Well, we have a generator now that we trained it, so we can use it. So we sample the generator and select the good test, whatever that means. And then we just add this to our test suite and proceed as long as we're not satisfied or as long as we have budget. So this is the big idea. Use the generator to propose new tests. Of course, this what I just described is vague. Like what does it mean that we include high fitness tests? And about that, I don't have the time to talk really. So you have to look at the paper. But another issue is that what does the good mean here on this line? And I'm going to tell you something about that, just to give you some ideas. So like, what does it mean that a candidate test generated by this generator is good? We just don't want to select arbitrary stuff. It could just, I mean, we somehow need to drive this G into learning this set of, or the distribution on high fitness tests. So not everything is good here. And how we do it, what do we mean by a best or a good test, is the following. So we train an analyzer. So it's an auxiliary machine learning model, could be a neural network. That's what we use. And what we really just do is that we use the random sample or the test suite to learn the mapping from tests to their fitnesses. We have data for that, so we can do it. And then once we got this analyzer trained, it can estimate the fitness of a test without executing it on the system under test. Of course, it might not be perfect, but even some partial information is good here. So let me describe the algorithm again with some additional details. So first we sample some random test suite of n samples. And while we still have budget left, we do the following. So we first train this generator on high fitness tests from this test suite, whatever this high fitness means. Then we train the analyzer on this data we have so far. And then we start to sample this generator for tests. And we basically sample a batch of tests, and then we can estimate how good they are using this A. And now this step, we get some information how good the tests are, but we don't have to do any executions on the SUT. So this is a crucial point. Then, okay, we select the test with the best estimated fitness, obviously. And then we execute this selected test on the SUT to learn its actual fitness. And then we add this best test to our test suite, and we keep going until we're satisfied. And an important point here is that is this line. So we really need to execute this test we selected on the SUT to learn its true fitness, because otherwise this training data we use for this analyzer could be garbage and it might be unreliable. So that's also very important. Well, we don't get stuff for free. That's the point. And yeah, the other issue is that what high level, or not high level, but what does a high fitness test mean, and how do we train the generator using it? And I don't really have a time to tell you how this is done. It's briefly that we make a training batch and we sample tests from the test suite to it randomly, but not uniformly. It's just in a way that high fitness tests have higher chance of being included. But yeah, you need to look at the paper for that, or ask me some questions later. And the intuition here is that over time, this analyzer should get more accurate in predicting the fitness. And this should mean that more high fitness tests get included in this training batch. And hence, as G is trained on high fitness tests, it should be able to produce samples from this set of challenging tests. I guess that's fairly obvious what we're after here. And yeah, I'll skip that. And yeah, of course, that's just an idea, and cannot really prove things. But for this, we devised some experiments. I don't have the time to explain them here, so you need to look at the paper again for this. But well, let's just say that we have one experiment which indicates that we can achieve state-of-the-art performance with our ideas, meaning that in a way, these ideas, what we have, are workable ones. So that's briefly it. So thank you for listening. I'm out.